So it's great today to have Sasha Migdal, and he's going to talk about the duality of fluid dynamics and solution of decaying turbulence.
So my talk is by design addressed to mathematicians, but as there are at least two very well respected by me physicists, I will also add like explanations and interpretation for physicists. So I hope it will be interesting for both, because in the end, what I'm trying to prove, or at least present, is equivalence of turbulence to certain peculiar string field. It will be well defined, but it's not a usual one. So let me first describe what I call duality. The first introduction is that it is a very unusual situation in the fluid dynamics. Typically, we theoretical physicists have the basic theories like classical mechanics, statistical physics, relativity, quantum mechanics, quantum field theory were built in previous centuries. But statistical theory of turbulence doesn't exist. Only basic equations exist. It's like we would know Newton equation, but we would not know Gibbs distribution. We need analog of Gibbs distribution for turbulence, because all we have is time dynamics, and we have yet to derive analog of Gibbs distribution. So there are some phenomenological models which don't really solve dynamical equations, but just make some assumptions in a hope that they will stick. They didn't stick. It was done 80 years ago, and they are not confirmed by experiment, and especially in case of decaying turbulence when there are no external forces. Kolmogorov laws don't. So this theory, the replacement of Gibbs distribution, must be built from Navier-Stokes equation, like Gibbs statistics was built from Newton mechanics, or the field theory was quantized by Dirac Feynman sum over histories of classical field. In both cases, the original theory already existed. It was a matter of computing the sum over paths or statistical sum. The definition was there. Here, we don't have definition. So turbulence statistics must emerge spontaneously from some internal symmetry without ad hoc stochastic forces added to Navier-Stokes equations. So this talk presents new perspective on fluid mechanics leading to such a statistical theory of turbulence. By employing the loop equation, we reformulate fluid mechanics in spatial dimensions more than 2 as a singular one-dimensional problem, which sounds kind of too good to be true, but that's what I'm going to present to you. And it's for mathematicians to consider this a conjecture and prove or disprove it, or for a physicist to verify whether that makes sense for the physical turbulence. So this transformation from three-dimensional fluid mechanics, for example, into loop equation is based on the concept of rough initial conditions in the Cauchy problem for Navier-Stokes equation. These rough initial conditions arise from thermal fluctuations that are always present in any physical fluid. So there is no such thing as smooth initial velocity. There's always temperature fluctuation. So what we call smooth initial velocity in physics means sharp distribution around some initial velocity, and the width of that distribution is proportional to temperature. But still, it is evolution of statistical distribution from sharp one to something else. So the way to study that is to consider the Fourier of probability distribution or generating function, and the one I choose is what is called Wilson loop or loop average. It is exponential of some factor, imaginary factor, times velocity circulation. That's integral of velocity around the loop. And it's direct analog of what is considered Wilson loop in gauge theory with velocity replacing gauge potential. Of course, there is no gauge invariance here, so that's where analogy stops. I'm not going to wave hands around fixed gauge invariance. I'm going to address direct Navier-Stokes equations as they are. So this is a particular case of what is called Hopf function, because Hopf considered things like that before. He considered exponential of some integral over space of velocity times some source. The idea of source, of course, goes back to Schwinger. So you have exponential of integral of source times velocity, and that is a functional of source if we take specific version of the source, which is concentrated around the loop in space. So if you take this thing, which is called Hopf functional, but takes a very specific source, which is integral over the loop of delta, three-dimensional delta function of the point on the loop, that will provide, this integral will reduce to circulation. Of course, it's abelian field theory for the physicists, so you don't have to worry about non-commutative variables.
So the expectation.
May I make sure? So when you're like taking this bracket V0, so it means you start with a distribution of initial data V0, which has some probability.
Yes. You
evolve
so
Navier-Stokes,
here,
and then you average over all of these initial.
that's right. So here, like always in Hopf distribution, you assume there is some initial field, which is also rough. Have some distribution of initial field, and you are studying evolution of that distribution. So this thing is generating functional for correlations of velocity field. What I'm saying is you could consider a subset of this functional, which is only functional of the loop by considering the source, which is concentrated on the loop. Then you will get what is known as Wilson loop as a functional of the shape of the loop. Yes.
Is theta the arc length, or is it an arbitrary parameter of the loop?
The loop is arbitrary.
I know, but what is theta? Is theta the arc length parameter along the loop?
Oh, theta is parameterization of the loop, but the whole integral and everything will be parametric invariant, so it does not matter. So you could say the loop is a map of unit circle in three-dimensional space, so theta is angle on that unit circle. So it's C prime of theta times d theta. Because this, by definition, is parametric invariant, you could reparameterize theta by any monotonous function of theta, so it does not matter how I choose. And that's a very important part of the whole approach, that equations will be explicitly parametric invariant.
Now, excuse me, though, the V that you have there, the V is not the same thing as the V0.
V0 is initial.
This one has evolved.
V0 is velocity field at initial moment. Once you have velocity field at initial moment, you could, in principle, compute that generating function. Say if it's some Gaussian distribution, it will be rather easy.
Yes.
But in general case, given initial velocity distribution of initial velocity field, you could compute this integral, which is linear function of velocity field.
Yeah.
And then you could compute
But what is the V of R there? Is the V of R what you get after you've evolved it for some time, or I don't quite?
Yes.
V naught is initial
Yes.
value, and then V, by definition, evolves with time according to Navier-Stokes equation.
So there's a
we-
time
You don't
variable
want-
which
you
is
don't-
missing.
You don't want to let it go evolve too long, because then if it's going to go to zero, right?
you could start at zero in principle, but at zero, if it starts at zero, it will stay at zero.
No, I mean, does that V of R depend upon T? That's what I'm asking.
Yes.
Yes, okay, you don't have T parameters there.
How long did you
Depend upon
evolve?
T.
How long do you
V
need?
naught is some distribution,
Yeah.
and C is independent contour, which doesn't depend on time, doesn't depend on V naught, is a just
No, I'm just asking with that a lot, but I mean, Camille's saying yes, so I want to be sure. So the V of R that you have there is really a V of R comma T. It has some time.
yes. I don't mention T because everything depends on time according to Navier-Stokes.
Okay.
So V depends on T
I just want to be sure.
and psi depends on T.
No.
So psi depends on T
Okay.
through V.
That's fine.
So
Sorry, what's the measure that you average over? So you average over V.
equation doesn't depend on that measure. Equation which I derived does not depend on.
You evaluated some average over V0.
That's right. The measure with which I take that measure, the average does not enter the equation. I don't need to specify that measure when I derive this equation. Miracle.
So when you had this notation, does it depend on the?
No, result depends. So solution of equation depends on initial value, and through that, it depends on that measure. So though my equation, which I will derive, I will answer your question in a minute. I will derive equation for psi, and the initial value for that equation depends on the distribution of initial velocity. So to define things, well mathematically. Otherwise, if I will use functional derivatives, mathematicians would spend the whole remaining of my lecture demanding from me to define what space it is, etc. So I don't want to do that. Once I discussed it with my good friend Alex Schwartz, he recommended me to just eliminate all the complex things from your talk if you want to have a chance to finish. So I replace the loop by a polygon with n vertices, and that n will tend to infinity. It's not like I'm going to take very large n and say it is large enough. No, I'm going to analytically find solution for arbitrary n and then tend n to infinity in that solution. So I replace loop by a polygon. So circulation is sum of delta c times v of c, or ck are vertices of that polygon. And correction is 1 over n. You could estimate correction because if you consider the circulation is integral of by Stokes theorem of integral of vorticity over area. So the difference between the polygon and the loop is just these little pieces of the loop which are between the neighboring points of the polygon. So these are small corrections, and therefore you could estimate it as 1 over n. Why? Because you assume in Navier-Stokes, by definition, you assume that velocity is differentiable and vorticity is fine. And therefore, everything is kosher. So using Navier-Stokes equation for time derivative velocity at constant loop, we find the following equation. So we take time derivative of psi, it will reduce to time derivative of the circulation, and it will be sum of delta c times, and this thing in the bracket is just the Navier-Stokes equation, time derivative of v. So there's one term which is gradient, a curl of vorticity, and second term is cross product of velocity times vorticity. And of course, that can be written in arbitrary dimension. Now, that is exact formula. There is also a term related to pressure in ordinary Navier-Stokes equation, but that term drops out in circulation because it will be integrated over the closed loop. So gradient terms are thrown away, and the remaining can be written like that. So there is vorticity, curl of vorticity, there is velocity, cross vorticity. So that's exact equation. Now, what I'm trying to do now, this is the most important step. With the same O of 1 over n accuracy, I can replace this, for example, the first term, right? I could replace nabla by gradient with respect to the one particular vertex. You could, that's by definition, because omega depends on this particular vertex, so you could take a gradient with respect to that particular vertex. Now, then, so you could get gradient k, which is derivative with respect to this vertex, times omega, cross omega. Now, omega k is a tricky thing. To get omega, you need to differentiate twice. Once you differentiate with respect to this vertex, and another time you differentiate with respect to difference between neighbors. You could also consider difference between neighboring vertices variables. So if you take a cross product of the second derivatives, it will just give you omega. Why? Well, if you differentiate circulation once, you will get a cross product of omega times the opposite side, right? Because the little area in the triangle, if you consider this triangle made of 3 vertices. When you differentiate with respect to these vertices, you get difference of these sides times omega, cross omega. So when you differentiate also on this difference, you will get omega. So that's how you get this formula for omega. So by just finite combination of derivatives, you will get omega in from the exponential. And the correction will be 1 over n because you neglect various terms. You neglect the terms with first derivative of gamma times first derivative of gamma, because first derivative of gamma goes to 0 because of the distance involved in the Navier-Stokes. Because the area, basically what I'm saying is that circulation starts with a little area, and here I effectively differentiate with respect to both sides of this vector area, vector triangle. So then you continue like that, and you find that this term can also be written in terms of operators. So velocity by Navier-Stokes, that's called Biot-Savart. It can be written as, again, as combination of that's the same operators up to 1 over n. So in my paper, I estimate errors and explain, but that is a well-defined statement. It's not something where I assume some hypothesis on some spaces. It's just finite number of vertices. I take derivatives and I estimate at large n the correction to Navier-Stokes equation. That's very important property of Navier-Stokes equation, that every can be reduced in terms of derivative with respect to the position of the loop. There is nowhere I would actually have the position of the loop by itself. So what happens is that we get the equation like that. Time derivative of this psi will be equal to some operator applied to psi. Now this operator will be sum over delta c, sum over delta c, and this will be some operator which only depends on gradients. And this operator is what I wrote. So if you look at that, you have quantum mechanical system with n vector degrees of freedom, and your Hamiltonian essentially only depends on canonical moment. It doesn't depend on canonical coordinates. It only depends on gradients, right? So what that means is that you could solve that equation by means of the superposition of plane waves. I want to stop here, and people may ask questions because that is the most important point.
The LK is the derivative in the K.
The LK is some functional of derivatives. For example, here it has a derivative here, and in omega k it also has derivative. Here it has non-local functional, which is 1 over Nabel square. So it is non-local function of Nabel. It is something which is expressed in terms of gradient, but not locally because of velocity. Velocity has 1 over Laplacian. And don't be scared by inverse Laplacian because it will become algebraic in a minute. Because we're going to take Fourier.
But your nabla K is differentiation in the CKs, right?
Yes, I already defined what is nabla K. Nabla K is differentiated with respect to CK, and eta K, which is another factor, is differentiated with respect to difference. There are two sides. So when you differentiate over CK, you get difference delta times omega. So in order to get omega, you need to differentiate, have mixed derivative. One derivative with respect to CK, another with respect to delta CK.
Why is VK called VK?
Huh?
In what sense is VK? Is that the relation between the velocity and the vorticity?
Yeah.
Yes, divergence of velocity is 0, and velocity and curl of velocity is omega.
Okay.
So if you take Laplacian of velocity, you'll get curl of vorticity. Yeah. So you could also write it in a very familiar form as an integral, of course. It's integral of omega of shifted points with the kernel, which is 1 over r minus r prime cubed. So it's it's nothing mysterious because it's one variable.
What's the one variable? What's the one variable?
The one variable is CK. So you have to shift in Fourier space. It will be operator which shifts CK by some constant, and that would shift coordinate of r of omega to some call. It will be some kernel.
Okay, but it is essentially the Biot-Savart.
It is
Yes.
Biot-Savart. It's the way to write Biot-Savart. It is just the Biot-Savart, nothing else. And of course, that looks very scary. But for those who are familiar with Fourier transformation, the more scary it is in coordinate space, the better it is in Fourier space. So this operator L only depends on nabla, which means that you could solve that equation by means of the Fourier transform. So you have ansatz, which solves this equation, sum of delta CK times some PK, momentum, and then it has to satisfy the momentum loop equation. So it's that same equation where where gradient of over delta C is replaced by P, and gradient of C is replaced by delta P. You know, if this same thing can be rewritten as sum over C times delta P. So you could find derivatives with respect to CK, and you also can find derivatives with respect to delta CK. You see my point? It is a periodic function, and you have complete integral. So you could replace it with the minus sign by sum of CK times delta PK with the minus sign, because it's integration by part, summation by part.
So did you say this is an ansatz?
Well, here's a statement for mathematician. This solves loop equation if P solves this.
The formal state.
Well, you substitute that, find time derivative, substitute time derivative by this, and you will get every term in the Navier-Stokes equation.
So find the pk via some transform.
It's not transform. I'm not doing any multiple integration. I'm just saying it is exponential.
I thought you said you're going to do
Well,
a Fourier transformation.
Yeah, it's a. I mean, you've got to find this pk.
No. P is, I am averaging over all solutions of this differential equation. So for every solution of this differential equation, this exponential satisfies that equation. What I'm trying to say, if you have this exponential, where pk satisfies this equation, then psi will satisfy this equation.
Yeah, okay, that I got, right? I mean, but if you want to kind of link it to the previous guy, you have to match the initial data that you
That's it.
got.
I didn't say anything about
And
initial
so matching the initial
data
data
would involve Fourier transform. You're right.
involving a Fourier transform
Yeah, that's
to
right.
find it the pk.
Yes, if you want to solve this loop equation with initial condition, then you have to transform initial
Condition into this.
initial value of psi to Fourier space, and you will get initial distribution for P. Yes, but I'm going to solve at the moment this equation with a boundary condition. I want to solve this equation with condition that at time goes to infinity, it goes to 0, meaning that psi goes to 1. Because decaying, there's theorem in turbulence, right? Energy is dissipating. So if you don't have any external forces, eventually the fluid will stop. So the physical solution is the one where velocity goes to 0. If velocity goes to 0, that means psi goes to 1. And that, of course, is a solution. That's a fixed point of equation. So we're looking for solution which approaches that fixed point. So that is another way of setting boundary condition, not at t equals 0, but at t equals infinity. So if we do that, we have to solve this equation for P. P is a n vector variables. P is a loop. P is also a polygon with n sides, kind of dual polygon. Like P, you could be associating P with the middles of the side.
Oh, so this is.
Yeah. So if you now let's look at this horrible equation. It's not as horrible as it looks. First of all, it is algebraic. Second of all, it has very simple time dependence. Here we have time dependence of P, and on the right you have homogeneous rational function of degree 3. So I have time derivative is scales as P cubed. That means, well, this is third degree, right? This term is also third degree. This is second degree, and so is this one. And this is 1, so it's the whole second term is also third degree.
Oh, I see.
So if you look for the power-like solution, it immediately can be found. And so there are, now let's consider the general possibilities. So this psi belongs to the unit circle because it's an average with positive measure of exponential factors. So every physical value of psi is either boundary of the circle, which corresponds to single classical solution of Navier-Stokes, or some point inside. So we'll start with some noisy data at t equals 0. And we're looking for a solution which goes to this fixed point. this cycle 1. And indeed, there is a solution which approaches this fixed point as time to the -1/2. If you time the derivative of time to the -1/2, you get time to the -3/2, and that matches the power on the right. So it's not approximate solution of large time, it's exact solution, some arbitrary constant T naught. It's a special solution, but we call it fixed trajectory. In other words, it doesn't satisfy any given initial condition, just satisfies the boundary. Now, so that's the solution which we're going to study, and we're also going to study a hypothetical solution, which would correspond to singularity at finite time. You know, there was a lot of excitement in the mathematical community for the last 20 or 30 years because there were a problem called millennium problem. I don't claim I solved it. What I claim is that my solution, if proven and justified, take it as a conjecture, doesn't have, my equation doesn't have blow-up solution. It's very easy to prove that if I introduce noise, therefore, if my solution, my equation applies, then I can prove that such a solution with singularity does not exist. But for mathematicians, that would be an interesting step towards really proving the problem. So that's one of the two results I'm going to talk about today. A second one is explicit solution for decaying turbulence.
So are you gonna tell us later about how you distributed your noisy data?
Yes, I don't have time to go into detail, but basically what you have Gaussian distribution around some initial field. Take arbitrary initial field and add Gaussian noise.
Yeah.
Say with certain sigma. At every point in space, there is a noise with certain width. Then you could compute actually that path integral, which could be computed for free. But it's a technical thing which is in my paper, which is published in the archive. I don't want to talk about
That's the initial condition.
Yeah, initial condition is not something very important for me at the moment. So here is the most important thing. Here is the solution for this decaying turbulence. It's 1 over square root of t plus some constant times something which doesn't depend on t and satisfies the fixed point equation. So time dependence exactly passes through the equation. F is still a polygon, but it does not depend on time. Time only is involved here. And then you will get the following vector equation, which of course is a recurrent equation because it's valid for every k, right? It's delta f means delta fk, and f plus means fk plus. I just skip the index k because it's local. It's valid at every point on the circle. You may say that I'm solving the equation where delta f is discontinuity of the function, and f plus is the principal value. Technically, in the limit when n goes to infinity, that is it. But I don't want to go into this slippery definitions of the curve which has discontinuity at every point. But what I say is that as recurrent equation, it makes a lot of sense and it can be solved. Here is the solution. I found the general set of solutions of that equation. This solutions for fk involves variable beta, which is rational fraction of 2 pi, and variables sigma. So it is some kind of random walk on a circle, if you want, because this describes a circle, and this formula for the radius of the circle corresponds to what is to unit. So it's a circle with, it's called regular star polygons with certain rational angle in terms of 2 pi and unit side. If it has unit side, then the radius is large, 1 over sine beta over. So what happens if you simply substitute this fk into that equation, use elementary trigonometry, you will find that equation is satisfied. Not like I'm approximating or throwing away terms, it's exact solution of that equation. And what is interesting is that it is random walk. So the condition between this alpha k and alpha k plus 1 is that the next one is the previous one plus sigma, which is plus minus 1 times this rational fraction of 2 pi. So it is a random walk on a circle. You could go back and forth. After n steps, you have to come back at original point. So it's a periodic random walk. So this thing with arbitrary sigmas and arbitrary p and q and arbitrary, nothing else is arbitrary. N is what is my parameter. So parameters are sigma k plus minus 1, Ising variables, and then it is also rational number q. There is also omega, which I didn't write here, which is you could rotate that whole vector because the equation is rotationally invariant. You could take the whole vector and rotate it in any direction. So
That would be a constant though. That's just one
global rotation. Yes.
Not a k dependent.
And that, of course, just drops from the equation because it's rotationally symmetric. So we call this Euler ensemble. And it was studied then in my paper and then also in paper of one of the postdocs who's sitting here, Bazak and his Professor Zacharescu, which was quite helpful for me because I learned some things which I didn't know about number theory. I learned them from Peter Sarnak, from my other friends, and I learned from everybody. Asked all mathematicians I know, and I eventually got some knowledge. And being totally ignorant of number theory, I derived some new equation. And then when I asked about that new equation, it turned out it was not known. So I kind of involuntarily made some tiny discovery in number theory. But that doesn't matter. The thing is, I'm just explaining how I arrived to that equation. That's a simplified version of that equation. Both terms must vanish, and these terms are solved by regular star polygons. These are simplest regular star polygons. This is for beta equals 4 pi over 5. That's a 5-point star. This is 8 pi over 17. And you could increase number of vertices. So this self-intersecting polygon, it's not what's called regular polygon. Regular star polygon is not the same star polygon. So it's very well-defined object. And what I claim, I reduced turbulence in Navier-Stokes to random walk on set of star polygons. Random walks is known for 2 centuries. Regular star polygons are known for 5 centuries, but nobody solved random walk on regular star polygons before, which is kind of funny. So I had to do it myself, the best I could. And I derived some new number theory identities for sum of powers of cotangent of fractions of pi. And Peter can confirm that, to his surprise and to surprise of myself, we didn't find anybody else solving that problem before. There's a beautiful finite formula relating the sums of powers of cotangent to what's called Jordan multitotents, or Jordan totents, which are expressed in terms of prime numbers. So here is the delicate point. Now I want to sum or average over all solutions. So how would you sum? You have a manifold. Mathematicians will say every element of this discrete manifold should be counted with equal weight. That's symmetric natural weight. That's what I assume. But if you start from Navier-Stokes equation, you don't know that. You have to derive, and that's analog of ergodic hypothesis. In case of the Gibbs statistic, you start from Newton equation, and then you arrive at energy surface. You say, okay, energy surface is invariant surface. It passes through so-called Liouville equation or Hopf equation. So, but who's proved that distribution of states of your states over the energy surface is uniform? That's called ergodic hypothesis, still unproven, but physics cannot wait. So I just make similar hypothesis here, and then I wave hands to explain to my friends physicists why is it natural. It is natural from the point of analogy of this solution to the string theory. And let me describe this analogy. Let's consider Well, first of all, for mathematicians, so the equivalence of strong coupling phase of fluctuating vector field to the weak coupling phase of random geometry in smaller dimensional space is a known duality phenomenon in gauge theory. So it's called ADS-CFT. In that case, it was conformal field theory, vector, well, whatever, vector field, is equivalent to some geometry in ADS-CFT, and the correspondent was not like unique space to space because it was boundary value of the conformal theory, which was related to this ADS. So here we have similar duality. Duality does not mean that dynamic variables are related. That's something very unusual. It's only that correlation functions are equal. So there are some situations in physics when a strong coupling correlation function in one phase corresponding to strong fluctuating field are equal identically to weak coupling phase of another theory. So correlation functions are equal, but there is no direct relations between variables. That's what is happening here. Because initially you have a velocity field and vorticity field which will fluctuate in three-dimensional space, and now we are expressing it in terms of statistical sum of the ensemble of the Ising variables on a random regular polygon. Now, what does it mean from the point of view of string theory? Target space is made by all the regular star polygon with arbitrary angle, which is parameterized by coprime numbers p and q. So this I call them fermionic degrees of freedom or Ising degrees of freedom are just associated with every link. So if you look at the Wilson loop, it has exactly the same form as a dual amplitude of the string theory. You have summing over all regular polygons, like functional integral of, you have a closed string, you have integrating over positions of that string, and that exponential, which I had in my Wilson loop, is exponential. It's like dual amplitude, where the coordinate space is this P momentum space, or F, and original loop plays a role of external momenta for this string. And the summing over all configurations in target space reduces summation over all fractions of P over Q. So now I'm reminding you that in string theory there is no ambiguity. When you have a functional integral, or in my case, sum of the configurations of string theory, you don't have arbitrary weight. You have kind of whole object, and you sum over, because it's quantum theory, right? You sum over all states, and states are described as they are described. And so that's my hand-waving arguments why I should take all configurations with equal weight. So let me draw that string. So that's original string. That's normal string with just Euclidean target space. It's equivalent, its world surface is a torus. And here, if I put all these regular polygons one after another, ordered by the value of beta, here we'll have some beta corresponding to like 2/3, some small ratio of P over Q. And the closer you get to this singular point, the larger will be the denominator. So here I bounded by denominator to 100. So the maximum radius would correspond to P equal 1 and Q equal 200. And the minimal, another equivalent radius will be P equals 199 and Q equal 200. So these are equivalent points, there is symmetry. So that is, and oh yes, and this red green are Ising variables, plus minus 1.
What are the coordinates of this plot?
Say it again.
So okay, so in this is this a two-dimensional plot?
Well, it is a three-dimensional,
It is a
it is a torus. I mean, it is topologically a torus. Well, it is.
Right, but what
I did, I just drew on the torus one regular polygon after another. So I put them at angular distance, equidistance, angular distance, like 2 pi over number of polygons. So I put them all on the torus, and they now become a tube. But if you look closer, you'll find out this tube is made of neighboring polygons. It's not smooth at all.
Okay, but so how do you arrange them on the poly? I mean, what is the? I'm just trying to figure out how it relates to. So you're putting a structure on this space of polygons, right?
I'm just saying
So that it becomes a
the
manifold.
global description of this space of polygons is this surface made of all polygons one after another ordered by the angle. Yes. If I take all the polygons ordered by the angle and draw them in space, there is some origin and they are drawn in space. Each one is in radial plane, so it's like I took
I understand. I
took
understand.
a tube and I just bended that tube so make it close. That's how I drew
And
this.
the cross section of your tube is the polygon
That's right.
at the place where you are.
And the variable tau variable going around the tube is angle on the polygon. And the variable counting the polygons is just the beta. So beta goes here and theta goes here. Theta goes around the tube and beta goes along with. So this is
Is this a blow up of the cross section?
what?
Is this disk that I see there just a blow up of the cross section?
Well, in principle, it's infinite. I limited the number Q by 200.
I think it's a very big cross section. I mean, the cross section is varying, and I think
Yeah, but I mean,
Because the radius of each polygon, they're not the same radius. They have equal sign, but the radius is growing like 1 over sine of beta over 2. So the smallest beta has largest radius. That's this.
Okay.
That's okay.
And also symmetrically, the beta equals n minus 1 has the same radius. It has a symmetry. So as my states are discrete, I could just order them. Then there is no functional fluctuations. It's just going around this thing, counts all of the states. So that's I allowed myself a poetic image that were not just computing correlation function of decaying turbulence, were revealing its hidden identity as discrete string theory, the beauty of primes under ugly mask of chaos. So because if you look at that,
Really, there's no primes here, right? There's
Huh?
only P and Q are relatively prime. There's no
yes,
prime.
they're co-primes, but counting them, you use Euler torsions,
Yeah,
which
yeah.
express that in a product of prime factors. So
Yeah.
it is about primes, yes. Yeah, well, co-primes is a very tricky thing. They exist all the way to infinity.
No, I'm just saying P and Q aren't primes themselves.
Yeah, co-primes. Yeah, co-primes. Well, yeah, it is about primes. So let me now tell you what happens in statistical limit. Now we want tend n to infinity. And in the limit of n to infinity, some part of that can be computed analytically. Another part, which is this one, summing over all coprime P and Q, does not have any smooth limit. It is calculable, but it is not smooth. And that's the beauty of it. So this thing at large n is calculable, indeed, but it's not smooth at all. But this random walk becomes continuous Gaussian Brownian motion. That's very easy. You could prove without much effort that random walk with steps plus minus beta in continuum at large n becomes integral over trajectories with ordinary Gaussian measure. So that is at large n equivalent to original random walk with steps plus minus 1. So, and then this S is something very explicit. It depends on the original loop. So that you may say is my expression for dual amplitude. So C prime is like external momentum, and e to the I alpha is the positional loop. Actually, e to the I alpha divided by this factor, because that's radius of the loop times e to the I alpha, that's the position of the loop. And so you may say that e to the I alpha divided by this is the position coordinate of the string, and C prime divided by this is external momentum. Then it's exactly the dual amplitude with distributed momentum on the loop. So, but don't forget that we have viscosity in denominator. The whole problem of turbulence was that viscosity goes to zero, and viscosity doesn't enter in denominator in original approach. In the Navier-Stokes theory, expansion parameter is 1 over viscosity. It's called the Reynolds number. Here we have something opposite. In the dual theory, viscosity enters in denominator, and therefore all we need to do is find quasiclassical solution, instanton. So we have to find this path integral in the limit when nu goes to zero, small enough, and then there will be some classical solution, and then there will be some fluctuations around this classical solution, and determinant of that fluctuations is also very important, but not the further terms. So you could compute leading quasiclassical approximation over the instanton corresponding to this classical action when viscosity goes to zero. Now, what we find out is that, first of all, it's trivially solvable. If you just say, for example, have a circular loop, then it's very trivial to find. Actually, for arbitrary loop, you can find. If you find the extremum of that action, you will have extra I here. So you'll have to find the alpha such that this product C prime times exponential of I alpha is real. Right? It means that alpha is pi over 2 minus argument of C prime. So it's solvable. It's solvable because an argument of C prime, by the way, is parametric invariant. That's a beautiful thing because the parametric transformation multiplies C prime by some real number. Therefore, argument of C prime is parametric invariant. So this thing is analytically solvable, and that is part of the solution. So the remaining problem is actual number theory problem. And I think I have to kind of skip that part because maybe I'll have discussions with my friends from number theory about details of that, because there are little details which all matter for professionals, and I'm just an amateur. But anyway, here's my amateurish approach. So I take this variable and I find out that there are certain sums, formula for the sums of this variable. So this sums divided by number of terms, which means average of distribution of x, they reduce to certain ratio of zeta functions. That's the result of my exact calculation. And then if you look at that, then you could do inverse Millian transform, and then you could find distribution. And the beautiful thing is that this distribution is quite non-trivial. Here's how it looks. It is x to the 3/2 times sum of phi of q to 1 to the integer, to the floor of 1 over pi square root of x. So this is a function which is not continuous. It has finite support because x cannot be larger than 1 over pi squared. Therefore it is finite. Locally, it has derivatives like this straight line, but at very small x, it becomes, it approaches square root of x. So it is what it is. You don't want to replace it by anything because it's not smooth. But you could compute things with that. So that's what I did. And I found, now I skip something because for my friend physicists, they could look at the paper because it's a tedious calculation, but in principle, it's all about computing classical solution, fluctuations, and that's something which modern postdoc in quantum field theory can do even better than me, I think, or maybe as good, at least. So you see this configuration, this specific loop has 2 points. So it's n and m, because there could be n steps here, m steps here when you replace a loop by some number of steps. And you have to sum over these variables. Let me skip these technical details. So when I do all that, I find something very interesting thing, which is observable thing. It's called moment of velocity. So velocity at one point minus velocity of another point squared, averaged over all these fluctuations. And I find explicit formula. That explicit formula involves ratio of zeta function and also involves some coseconds and then some rational factors. And this function f is an entire function, which means that it doesn't reflect on the poles of this V. And the poles of this V determine what's called the spectrum of decay indices. So this is a funny example that in turbulence I can compute the spectrum exactly. It's easier. It turns out to be simpler than critical phenomena, where the spectrum is only computed numerically using so-called conformal bootstrap. So here is exact spectrum. So it involves 2n, where n is more than 1, 5 halves, 11 halves, and 7 plus minus I times imaginary part of the zeta function. So there are, complex poles. Why complex? Because it's not a conservative system, it's decaying system. So normal thing, there should be oscillations. It's a quantum system in my approach. So these oscillations reflect quantum consolations, and that is something very exciting. It's macroscopic quantum phenomenon. Also, for the physicist, I can claim, maybe that's too bold of me to claim, but that's the first manifestation of string theory in nature. Well, that's of course a stretch. But anyway, it is something stringy, which is yet to be compared with the original string theory, but that is three-dimensional turbulence, which is measured, and it exists. So in gravity, it's yet to be found what kind of string theory really describes reality. Here is quite specific and totally crazy. And by the way, string theory doesn't exist in 2 or higher dimensions, but this is less than 1 dimension, it's discrete system. So there is no problem here related to the divergence of fluctuations around things. So this is similar thing for the energy spectrum. So no, energy is a function of time. And I singled out with a red color minus 5/4. Minus 5/4 is a leading index of decay. That means that energy, if you pass the fluid fast through the oscillating grid, its energy decays with distance or with time, because the time is proportional to the distance. Distance is proportional to time passed. So at every given moment in the flow, there is energy decay, and in terms of in the system of coordinates where the grid is fixed and the flow is passing, it is just the distance from the grid. So it decays by the law of time to the minus 5/4. And that's very interesting situation, because this thing was measured in physical experiments in 1966. And since that time, Kolmogorov theory could not obtain that value. It exactly obtained 5/4. In Kolmogorov theory, with some model approximations called Softman, etc., and some stretch and estimates give something like 1.2, 6/5, which is not correct. I gave exactly 5/4. That matches experiment within experimental error. And then, of course, let me show you the most impressive plot I have. I computed this second moment, which is difference, average value of velocity, difference velocity squared, as a function of one variable, which is r divided by L. And L is length, which I measured separately, which is proportional to square root of time. So it's scaling function of 2 variables, but it actually collapses on a function of 1 variable, which is r or L divided by L of t, square root of t. And that's what I call effective index, logarithmic derivative of the second moment. So this blue line is what Kolmogorov predicted. It must be equal to 2/3. And I'm done, almost.
Now, could you explain, I don't understand the
So
horizontal
this
axis
is
here.
r divided by square root of t. So
So-
it's a logarithmic variable. Okay. So it's a log scale. So this horizontal axis is logarithm of distance between
Yeah.
points
Yeah.
divided by square root of time.
Okay, divided by square root of time, okay.
Yeah. So Kolmogorov says it doesn't depend on scale because it is scaling laws. This is already logarithmic derivative. So Kolmogorov says it is equal to 2/3, which is 0.66. Now, my theory produces this green curve. And numerical simulation produces this red dots. And the red dots perfectly match my theory and are totally violate the Kolmogorov scale. The Kolmogorov scaling does not correspond to experiment, and my theory does.
If I look at the
Where's
cubic,
experiment?
if I look at the cubic one, they all match up at the cubic level? Velocity cubed,
Oh, I didn't compute it yet.
because they should match up, right?
You see, velocity cube, which is considered Kolmogorov relation,
Yeah.
has two parts. There is potential part of velocity, which actually determines velocity cube.
Yeah.
And there is a triple correlation of artistic, which could be totally different. So velocity cube is dominated by potential part, which is influenced by forcing. So it's not universal, I claim. So it's totally different. I cannot have no claims here, but I only consider the second. So now the most important other statement is this, that if you have my same equation, and now you're looking for the finite time blow-up solution, that would correspond to F, which does depend on time and has some singularity at finite time. You see, I had t plus constant to the -1/2. And now I'm looking for some constant minus t, which means this solution exists only up to some moment and then it blows up. Theoretically, such solution could exist, blow-up solution. But if you look at the equation for this function f, you'll find that this equation doesn't have solution because this coefficient, which must vanish, is positive definite. So either you have solution where f plus is proportional to, or f plus is proportional to delta f, that would be a solution with zero vorticity, but we know from the work of Pfefferman that singular solution must have infinite vorticity. So solution with infinite vorticity cannot have f plus proportional to delta f, and because vorticity is proportional to cross product of plus and delta f. So I can prove that it's a theorem, but it's not a theorem about original Navier-Stokes because I have to use my equation. So that means that my equation is valid at finite n, and my equation is valid at finite noise in initial data. So given that, as modification, I prove there is no explosive solution. So if mathematicians want to prove the famous theorem, they need to, in this approach, they would need to prove that two limits exist, n going to infinity and sigma going to zero. Sigma is a variance of initial velocity. So if those limits exist, then that would prove that there is no explosive solution. So that's it. Yeah, I'm just saying that that's what is to behave. It will have a pole, but if f cross delta f equals 0, then it will not exist. So that's basically all my talk. I can say that my main results is that classical Navier-Stokes equation reduces to one-dimensional equation. There is some non-trivial initial condition. Then there is the degenerate fixed point, which decaying turbulence presumably is covering that. I cannot prove it, but I say that solution at least solves Navier-Stokes equation. And we found this solution in quadrature, and it's a matches experiment. And then we found no explosion theorem for my equation, but not yet for Navier-Stokes. So that's it.
Explain a bit what you mean by matches experiment. What experiment and what are you predicting that matches experiment?
Experiments, so there were two kinds of experiments. So there were numerical experiments.
They're all numerical solutions.
No, they're both. There were physical experiments, I know at least two. And these two physical experiments measured this decay of energy by 5-4. In both experiments, I found exactly matched 5-4. So I derived this 5-4 without approximation. It's property of the solution. Now, I'm waiting now. My good friend Srini is actually performing now a large-scale numerical experiments, which would elaborate on that and consider larger. This corresponds to Reynolds number only about 80 instead of infinity, and this corresponds to lattice about 1,000 steps cube. Now, technically, with existing computers, it's possible to take like 24 cube lattice and reach Reynolds number maybe 10,000 or so. I should ask Srini about that if he's listening, I don't know. So anyway, that experiment is in progress, and so far they independently produced these results. So I have two DNS results for small lattice, and they both match this easily. Slightly similar, different Reynolds number, so they don't exactly match, but they both are within errors from the.
So to get this curve in your inverse moment problem where you have the Riemann-Zeta function, that's incorporated into.
That's right. So this green curve obtained by integrating numerically, yes, I use Mathematica and a lot of tricks to do complex integrations in complex plane. That's kind of, for me, that's a piece of cake. I just love these things. So yes, I did it with 4 or 5 digits in Mathematica. It can be done with arbitrary accuracy because there is a methods.
Yeah, okay.
So it's something which number theory might actually elaborate and do much better than I did. Because number theory is very experienced with these integrals involving zeta functions. So maybe if there is some transformation which will give much better.
Any questions? Yeah.
Around your slide called part 2, said you found this explicit solution to with decaying turbulence.
Yes.
How does this relate to the initial velocity distribution? So like it's an explicit solution.
It's a fixed point. It's universal. If it would be related, that would not be an interesting thing. It's fixed point. There is universal asymptotic regime, which is called turbulence. And at certain initial conditions, you reach that regime, and certain others you don't reach. If you have a small velocity initially, you stay in a laminar flow and you never have turbulence. But if you have a lot of vorticity in the initial data, then it starts decaying and then approaches the solution. That's what we saw in numerical experiments.
You have a condition on a condition on the initial velocity distribution.
I did not derive the condition under which I get. It's like if you look at that, you see, if you look at that, in the beginning, I had this complex unit. It's in the very beginning. Yeah, this. So that is the physical region of Wilson loop. It's inside the unit circle. It's complex number, which is by absolute value less than 1 because it's average of the phase factor. So I start with some noisy data. In the beginning, solution depends on that initial data. Then it approaches this universal trajectory, and then the universal trajectory leading to 1 is universal. I found it. I found that solution. It has arbitrary manifold, and I assume that I'm covering that manifold uniformly. That's a big assumption. That's like a ergodic hypothesis. I haven't proven that. It has some physical meaning because with string theory, you don't have arbitrary weights. You have just unit weights for every configuration, but still, I haven't proven that. So it's the same thing as start with Newton equation with initial data, and then you reach Gibbs distribution, right? Gibbs distribution doesn't depend on it. Same thing. And this solution is the one which will blow up, and I eliminate that. I cannot prove that you start from classical smooth solutions. Smooth initial data would correspond to the boundary of this circle. If there is only single velocity, then what I call psi is just phase factor. So it's on the boundary. So the unit circle corresponds to classical smooth initial data. So if I start with initial data, I cannot prove. But if I start somewhere inside, I can prove that that does not happen. And I see that sometimes this happens. Now, what part of an unit circle would end up with the universal decaying turbulence, and what part will just stay laminar, meaning nothing happens? I don't know. That's not something I can prove yet. I'm just saying it is a self-consistent solution which corresponds to decaying turbulence.
So for a certain time, you're not going to have universality, but then there's a certain time scale at which the universality is supposed to set in.
Yes.
Can you say something about that, or?
Yes, I can study it. I hope it is attractive. And then I studied small deviations from that fixed point also.
Okay.
I take this fixed trajectory, then I have small perturbations. I derived equations for the spectrum of decay indices. Turns out that corrections to this fixed point are not exponential in time, but power-like in time. And if I prove that indices are negative compared to what you already have, that means that that's a stable solution. And that's a solvable problem because I wrote explicit equation for that spectrum. It's just complex, and I don't know how to tend n to infinity in that equation. That's another beautiful problem, I think, for number theorists. Is Euler ensemble stable? There is a well-defined object, very well-defined statement. It's like Lyapunov stability.
Okay, his Euler ensemble is a number theoretic statistical model that he made.
So yes, this you could take solution with uniform covering, and within that solution you could compute the indices of the small perturbation, check whether they are, decaying or not. That would be a real answer to these questions. If I see it as a attractor, then I would say, well, that means in certain vicinity of the space around this attractor, I definitely am attracted by construction. So how far is this? I don't know, but at least this. So that's the missing part of my theory. The investigation of stability. Though formally equation is written, it's not considered in the limit of angle.
Very well. So let me encourage you to possibly continue the discussion at tea.